Hello all, let's start section 3.4. In 3.4 I will cover for you measures of relative standing. What does it mean, relative standing? First I'll put the definition for you. It means comparing measures between or maybe within data sets. If you remember in my previous lecture at the last part of 3.3, we tried to compare two different data sets, and the only way was that to first find the coefficient of variation, then compare them. What to do today is, with this lecture, we will talk about a new topic which we call it z-score. Z-score actually allows us to compare two different sets of data with each other, or even inside one set of data we should compare parts of it, or maybe a sample with population or a sample with another sample. This is what we call it z-score. First, very important to know what is z-score. We already know, we already use type of such a formula in 3.3, but we didn't name it. Today we officially named that formula, and after this we will use it as a z-score. What is z-score? Z-score means the number of standard deviation a data value is a way, data value, let's say what letter we are using for data value. All of us at this point, we know we use X for data value, correct? The number of standard deviation, a data value X is away from where? From the mean. You see, we covered this before. Sorry, from the mean. We covered this before, but now today we are going like more professionally and deal with this topic. If I ask you on the test day or inside the class, what is z-score, please do not be quiet and say, oh, you didn't give us the definition. Here you go. The number of a standard deviation, a data value X is away from the mean. We call it what? We call it a z-score. For example, if you remember this example, I used, I think in 3.3 this example. I will repeat it again here. Here you had 10. It was about the weight, right? Here you had 58, and of course our mean was 34. We were looking like, is 58, or on that example I was asking, find like what percentage of the data will fall within 10 and 58, correct? And on that purpose, you had to find how many standard deviation you're away. 58 is away from 34, or how many standard deviation 10 is away from 34. To put this notation for you, to explain it, this is your mean. I'll use X bar for sample. You can use mu also. Right now, in a couple minutes, I'll give you both formulas. They are the same, just notation is different. For example, this is X bar, your mean, and this is your data, X. 58 is X, correct? To find this distance, we covered this topic so many times in the class. To find this distance from X bar to X, we always subtract from X what? X bar, correct? Which here will give me 58 minus 34, which will gives you 24, correct? Now, this distance is 24, and the standard deviation for this problem S was given for you 8 pounds. Now, you were actually looking in that example, we did a different way actually. We went like added 8 on the top of 34 few times to see how many times 8 goes between 34 and 58. But if you see how many times 8 goes in 24, it's a division problem. It means if I simply divide 24 by 8, it will give me 3. Or I can say, what was 8? 8 is your standard deviation. If I create this formula that x minus x bar over s, that gives me the number of standard deviation that my data is away from the mean. You see, my data x, which is 58, is away from 34. It's 3 standard deviation away. Correct? Sometimes, look, if this number is not 58, here 8 went easily like 3 times to 24. Let's say you end up with 26. Then what will you do? If you just follow the process that we did in 3.3, okay, it goes 3 times and what? Correct? But if you use this formula, you divide 26 by 8, it gives you a decimal number. Correct? A decimal number, which is totally okay. Which is totally okay. I'll explain why. Correct? Then, using this example, I will create here 2 formulas for you. First, the formula for the sample. Correct? Z score, finding Z score for sample, and also here for population on this side. For sample, of course, we will use the letter Z for Z score. Z is equal. You already saw your data value always minus mean over what? S. Because S represents a standard deviation for a sample. X bar is the notation for the mean for a sample, correct? Now, if I want to create such a same formula for population, Z equals, X is always X, right? Instead of X bar, when you find the mean for a population, at this time you know you have to use mu. You know already all notations. Instead of S, we use the lowercase sigma, or even I named it for you a canon. Correct? Sigma, not canon. Some of my students, they say canon, it's okay. But it's sigma, lowercase sigma, which represents the standard deviation for a population. You see, the calculation of both formulas are the same. The math is the same. Only the notation is different because one of them represents Z score for population, the other one represents Z score for a sample. correct? Now, what z-score does, let's make a note here to know. I'll put a star here. Allows comparison of the variation in two different sample samples, or it can be what? Population. Correct? This is what z-score does for you. It allows you to compare two different sets of data. Which part? The variation in two different sets of data you can compare. I will do here an example. I copied this example from another professor's. I like his example. I copied. I didn't create this example. He worked hard on this example and I just copied. I like this example. Correct? Let's compare. This example will be about the height of two different people. And the first one, he used a data set from the height of the President of United States. I think he was the 36th President of United States, Mr. Lyndon B. Johnson, which we call it LBJs, correct? His height is 76 inches. He was, I think, the 36th president during Cold War. President of the United States. I think he was around Cold War on that time. And the mean for presidents, for all the presidents of the United States is given as 71.5 inches. All of them. It's calculated. Standard deviation is 2.1 inches. 2.1 inches. Correct? We are talking about all presidents of the United States. When I'm saying this data comes from all presidents of the United States, definitely we know we are talking about population. And we will use the population formula, not the sample one. They are the same. Calculation is the same. But we use the notation for population because we are talking about whole population, which is the presidents of the United States of America up to now. Correct? The next person that he selected to compare with is the famous basketball player. You know him better than me, Shaq. Correct? Mr. Shaq, or that player, his height is 86 inches. For his team, I think he was playing in Miami Heat, right? Mean for the Heat let me put capital H, it's the Miami Heat team, is 80 inches. And a standard deviation for this team is 3.3 inches. correct? Two different data sets. This is one of them. This is the other one. Here we are talking about LBJ's, President LBJ, and here we are talking about Shaq, which was playing for Miami Heat. Correct? Two different sets of data. Why we do this example, and what is the question actually? We want to answer this. Who is relatively taller? Who is relatively taller? Correct? This is the question that I want to answer. President LBJ is taller, relatively, or Shaq? In absolute, if I want to pick absolute, talking absolutely, definitely Shaq is taller than President LBJ. Correct? Because he is 86 inches. It means how many? 8 something? 8'4", 8'3", something like that. No, 6'4", something. 6'4". Actually, he is what? 6'4". And President is what? Same thing, 6'2", I think. This is 6'4". President is 6'4", but this one is divided by 6. Seven something actually. Correct? 7 something. If you divide by 12, 86 divide by 12, let's find how tall he was. 1 time 7 times 12 gives you what? 84, correct? 84. It means 7.2. He was 7.2, not 6.4. 7.2, which is a pretty high, right? It's really high. 7.2 is really high. If we talk absolutely, definitely Shaq is taller than LBJ. But who is relatively taller? It means we are comparing LBJ's height to his group, and here we are comparing the Shaq's height comparing to his group. Then we see who is relatively taller. Let's use our formula. First thing, I will use the z-score formula for LBJ's, correct? LBJ. Z-score is x. I will use mu because we are talking about population over what? Sigma. Your x is for LBJ is 72, 76, correct? Minus the mean for him, for the presidents, the mean height is 71.5, correct? 71.5 inches. Divide by their standard deviation. Their standard deviation is 2.1, correct? And if we calculate this, we will end up with how much? 2.14, correct? 2.14. That will be the z-score for President LBJ. If I do the same calculation for Shaq, correct? Then z equals x minus mu over sigma, which gives you 86 minus, I have to use the mean for this team. The mean for this team is 80, right? Over standard deviation for the Miami Heat is 3.3. and it gives me 1.82 if I do the calculation. Now, I can answer the question, who is relatively taller? Actually, President LBJ is relatively taller than Shaq. Why he is relatively taller? Because he was one of the presidents that he was tall enough. Great, 6.66664 something. He was tall, correct, compared to the other presidents of the United States. But for LBJ, you see, the z-score is smaller. It means the average height in the Miami Heat, they were really a tall team. Everyone was tall. I think in one point, Miami Heat was a team that they had really tall players. Correct? That's why you see, comparing the Shaq's height with his team, he's not that tall. But comparing LBJ's to all the presidents of the United States, he's taller. This is how the z-score allows us to do, to compare two different data sets. Correct? Now, a few more things that I want to talk about. First, let's answer this question. How do you tell what data is usual or unusual with z-score? We already know 68%, 95%, and 99.7%. Correct? If you watched my lecture, easily you can answer this question. Look, first, here is your mean. The variation always at the mean, the standard deviation at the mean is always 0. Why? Look at the president was 76 inches, correct? If the mean is also 76 inches, 76 minus 76 gives you 0, correct? Then remember, standard deviation always in the mean is 0. Now, here on this side, I'll get one standard deviation. On the left side, I get -1, correct? One is standard deviation on the left. Here, 2 standard deviation. Here, -2. Here, 3 standard deviation. Here, -3. Why negative? We are okay with z-score. Please remember this. This is your formula. X minus x bar over S, or over, if you use the population. Please do not do this. Oh, I end up with negative. Let me change their places. I will write x bar minus x. Don't do it. It's always x minus x bar. It's not x bar minus x. It's not mu minus x. It's x minus mu. Keep this in mind. I'm telling you a few times, do not do this mistake. Your formula is always x minus x bar over S. And you see, sometimes if your data value is less than mean, for example, if your data is 12 and your mean is 18, of course you end up with a negative number. Correct? That's why you can have a negative z-score. Now, hopefully you remember, between 2 and -2, 2 standard deviation away from the mean, we called our data what? Usual. Correct? 2 standard deviation. Between 2 standard deviation we called our data usual, which was 95%, right? Between one standard deviation from -1 to 1, it was 68% of the data. Everything out of -2 and 2 will be unusual. Correct? Then I'll put some notes to just memorize this, that you are, if I ask, is this data is normal or not? Just check it this way. We will do examples, but first some notes. A z-score between -2 and 2 is considered usual. I will put 2 double lines with the red color between 2 and -2 and here usual. If your z-score is between -2 and 2, we consider that data what? Usual. What about unusual? And usual. What is unusual? Less than -2 or greater than 2. This side, if I use green color, here greater than 2 or less than -2. These are unusual. These two sides. And usual. Correct? Let's practice with this. Example. Let's put LBJ into play in Miami Heat. President LBJ, I don't know he's alive or not. Usually presidents, they are not playing basketball, or if they play, at least not professionally. Let's put LBJ. Let's say LBJ plays for Heat, for Miami Heat. Is this usual? Is this his height is usual to play for Miami Heat or not? Let's see. Z-score equals x minus mu over what? Sigma, which we already calculated. It was 76 as height. The mean for Miami Heat was 80 inches. And the standard deviation was 3.3. You see 76 minus 8 definitely gives you a negative number. Correct? And if you subtract and divide, you will end up with negative 1.21. Is this usual to have such a height, 76 inches, to play for Miami Heat? How I should know? Look, if you see it in the graph, this is 0, here 1, -1, here is 2, and here is your -2. Correct? Of course, 3 and -3 is also on two sides. Our usual data was between 2 and -2 and 2. Where is -1.21? -1.21 is somewhere here, correct? Then it is usual. You can say, you will answer. It's usual that for someone to have the height of 76 inches to play for Miami Heat. It's usual. Correct? Another example, let's compare my height. Can I play for Miami Heat? Example, Mr. Ahmed wants to play this time. Correct? For Heat, for Miami Heat. The Z score, if I calculate, I'm like 72. I don't know, they tell me I'm 72. It's in my driving license. Maybe on that time I had hair. I was looking taller, but no, I'm not that tall actually. Maybe I'm 5 something, 5'10" or more. But definitely it shows like I'm 6 feet tall. I don't know. I don't know. Hopefully not. It's too tall. 72 minus 80 divided by 3.3. Correct? And if you do this calculation, again you will end up with negative 2.42. Is 2.42 is usual to play for Miami Heat? You see where I am. I'll use the green color. Negative 2.4. I will be somewhere here in this region in green. Then it's unusual. I am too short to play for Miami Heat. Correct? Based on the mean that they have in their team. I'm short. I cannot play for them. Right? Oh, I think I saw some players in my life at least that they're really shorter than this, but they played basketball. It can happen. It can happen in reality. But based on this calculation, it's kind of something unusual that someone is short but he's still playing basketball. Correct? It's unusual. You see it like unusual. Correct? But in reality, it can happen. Maybe there are so many players out that they are short, but still they are playing basketball. Correct? One more statement for this part of the lecture, then I'll stop the lecture and I do another part for it. You see here, you actually, we discussed it already with this example. The larger the Z score is, the larger the Z score is, in terms of absolute value, of course. Let me put that one. The larger Z score in terms of absolute value, the rare the data value is. Look, absolute value of negative 2.2. I use the word absolute value because if you go to the left side of your mean, all the Z scores are negative, but their absolute value is actually greater than 2, right? 2.42. Or negative 3. Negative 3, the absolute value of negative 3 is 3, correct? That's outside of negative 2 and 2, correct? As much as Z score grows bigger, the absolute value grows bigger and bigger and bigger, the value becomes what? Rare. Correct? We discussed this in 3.3 at the last part of 3.3. I discussed with you, like, out of 2 standard deviation, your data, we call it rare. Correct? This is an A here, rare. I will stop the lecture. See you all next time in the last part of section 3.4, and I will cover In the last point, we will talk about quartiles and we will talk about percentiles. Okay?